Ice disappeared, forests spread toward the poles. Oceans warmed, and life reshaped itself in the heat. This was not a brief anomaly. It was a world locked in endless warmth, where winter simply stopped existing. But a planet without winter is not a paradise. Because when heat becomes permanent, balance begins to break, and the forces that sustain life start to turn against it. To understand what followed, we must begin with the world as it already was. During the Cretaceous, Earth was not a cold planet waiting to warm. It was already a greenhouse world. Atmospheric carbon dioxide levels were several times higher than today, likely exceeding 1,000 parts per million in many intervals. This sustained elevated temperatures across the globe, with mid-latitude ocean waters exceeding 88 degrees Fahrenheit. There were no permanent ice sheets at the poles. Antarctica and the Arctic were not frozen deserts, but dynamic environments with forests, rivers, and seasonal ecosystems. Sea levels were also dramatically higher, by as much as 650 to 980 meters compared to today, submerging continental margins and creating vast inland seas. These shallow, warm waters reshaped coastlines and influenced climate patterns on a global scale. Across this landscape, vegetation flourished. Dense forests extended far beyond the tropics, supported by high carbon dioxide levels, abundant rainfall, and extended growing seasons. Life was not struggling, it was thriving, within a stable, long-established system. But stability does not mean balance. Earth was already warm, and then something began to push it further. This was not the beginning of warming. It was the moment the planet moved beyond its familiar limits. The shift did not begin with something visible. There was no single eruption, no sudden break in the landscape. Instead, the change began quietly, in the air. The key player was carbon dioxide. Invisible, odorless, and already present in large amounts during the Cretaceous, it was part of what kept the planet warm. But over time, its concentration did not remain constant. It began to rise. To understand why, we have to look deeper, beneath the oceans and further back in time, to the breakup of Pangaea. As this supercontinent slowly fragmented, the land masses that would become North America, South America, Africa, and Europe began to drift apart. Between them, a new ocean basin started to form, the early Atlantic. This was not a gentle process. The stretching and thinning of Earth's crust triggered intense geological activity along mid-ocean ridges. Magma rose from below, creating a new ocean floor in a continuous process known as seafloor spreading. With it came widespread submarine volcanism. Eruptions not seen, but constant and far-reaching. These undersea volcanic systems released vast amounts of carbon dioxide into the oceans and atmosphere. Over millions of years, this steady input began to accumulate. At the same time, rising sea levels reduced exposed land area, limiting the extent of forests that could absorb carbon dioxide through photosynthesis. Gradually, the balance shifted. The atmosphere became denser with greenhouse gases. Not dramatically at first, but enough to retain slightly more heat year after year. The oceans warmed, evaporation increased, climate patterns adjusted. There was no immediate tipping point, only a slow, persistent buildup. And with each passing million years, the system moved further from where it had been, towards something warmer, heavier, and increasingly difficult to reverse. By the time these changes had fully taken hold, Earth entered what scientists recognize as the Cretaceous thermal maximum, one of the warmest sustained intervals of the past 200 million years. This was not a brief spike in temperature. It was a prolonged state, lasting millions of years, during which the planet operated under extreme greenhouse conditions. Atmospheric carbon dioxide levels are estimated to have reached between 1,500 and 2,000 parts per million, several times higher than today. That concentration fundamentally altered how heat was retained within the climate system. Ocean temperatures tell the story even more clearly. In many mid-latitude regions, surface waters likely ranged between 95 and 100 degrees Fahrenheit. These were not isolated heat waves, but persistent conditions. The oceans, which today act as a source of cooling and stability, instead became reservoirs of heat. If you could stand at the edge of one of these ancient seas, the experience would feel unfamiliar. The water would not offer relief. It would feel closer to a warm, enclosed basin than an open ocean. Evaporation would be intense, the air above it heavy and humid. Even the poles, regions that today define cold, were transformed. Instead of ice, they supported temperate climates with seasonal vegetation and flowing water. The temperature difference between equator and pole was reduced, creating a more uniform but consistently warm global environment. And that uniformity mattered, because without strong temperature gradients, atmospheric and ocean circulation changed. Heat was no longer efficiently redistributed, it lingered. There was no refuge, no high-latitude escape from the heat, no cold season to reset the system. This was not simply a warmer world. It was a world where warmth had become the baseline, everywhere, all at once, and for longer than any organism had previously experienced. As temperatures rose and oceans held more heat, the effects did not remain evenly distributed. They began to reshape life itself, starting in the seas. For millions of years, marine ecosystems had been dominated by long-established reptilian lineages. Among the most successful were the ichthyosaurs, streamlined, fast-swimming predators that had thrived since the early Mesozoic, and the formidable pliosaurs, apex hunters equipped with massive skulls and powerful jaws. But under the conditions of the thermal maximum, this stability began to break. Warmer oceans hold less dissolved oxygen. At the same time, increased temperatures accelerate metabolic demands in marine organisms. For large, highly specialized predators, this creates a mismatch. More energy required, but fewer reliable resources. In addition, shifts in ocean circulation altered nutrient distribution, affecting plankton at the base of the food web. As primary productivity fluctuated, the effects cascaded upward. The result was not an immediate collapse, but a gradual decline. Fossil evidence shows that ichthyosaurs, already reduced in diversity by the mid-Cretaceous, disappeared entirely by the early late Cretaceous. Plesiosaurs followed a similar trajectory, their numbers and ecological dominance fading as conditions continued to change. Yet the oceans did not empty. They reorganized. In the ecological space left behind, new groups expanded. Among them were early large-bodied sharks, more adaptable, with flexible diets and physiological traits better suited to variable conditions. Their diversity increased, and in some regions, they began to occupy an apex role. At the same time, another lineage was emerging, the mosasaurs. Descended from terrestrial squamates, these marine reptiles began to diversify rapidly during this interval. With elongated bodies, powerful tails, and efficient swimming adaptations, they moved into niches once held by earlier predators. This was the first major turning point. The oceans were not becoming lifeless, they were changing leadership. What had been stable for tens of millions of years was giving way to a new structure. The balance had shifted, and once it did, there was no returning to what came before. While the oceans were undergoing a period of dominance, life on land followed a different path. There was no sudden collapse here, no widespread extinction tied directly to the warming. Instead, terrestrial ecosystems were reshaped, expanded, and in many ways, intensified. Under elevated carbon dioxide, plant growth was strongly enhanced. Higher carbon availability can increase photosynthetic efficiency, particularly for certain plant groups present during the Cretaceous. Combined with warm temperatures and, in many regions, increased rainfall, this allowed vegetation to spread across large portions of the continents. Forests extended into higher latitudes. Floodplains widened. In some regions, open woodland and savanna-like environments became more common as climate patterns shifted. The result was not a uniform landscape, but a mosaic, productive, dynamic, and capable of supporting large herbivores in unprecedented numbers. And where plant life thrives, herbivores follow. Among the most successful were the sauropods, the long-necked, long-tailed giants that had already dominated terrestrial ecosystems for tens of millions of years. During this interval, some lineages reached their maximum known sizes. One of the most striking examples is Argentinosaurus, a titanosaur from South America that may have exceeded 98 feet in length and approached 154,000 to 176,000 pounds in mass. Such size is not arbitrary. It reflects a system capable of sustaining it. When food is abundant and growth is not limited by seasonal scarcity, the upper boundaries of body size begin to shift. In these conditions, it appears that biological constraints did not disappear, but they were pushed further than usual. Yet an increase in herbivores does not exist in isolation. It creates opportunity. Large predatory dinosaurs, particularly theropods, also diversified across many regions. Groups such as Carcharodontosaurids and Abelisaurids occupied apex roles in different parts of the world. They varied in form and hunting strategy, but their presence reflects a consistent pattern. Where prey becomes more abundant, predator diversity tends to increase as well. This was not a peaceful expansion. It was a rebalancing. Ecosystems grew more productive, but also more competitive. Energy flowed through the system at higher levels, supporting both immense herbivores and the predators that depended on them. And this leads to a crucial insight. This was not a paradise. It was a new equilibrium, one shaped by heat, abundance, and constant pressure. What we have seen is not simply a story about heat, or even about dinosaurs. It is a story about how life responds when the rules of the environment begin to change. At its core, this moment in deep time reflects two fundamental processes: climate change and evolution. The thermal maximum did not act as a single event, but as a sustained pressure, altering temperatures, ocean chemistry, sea levels, and ecosystems over millions of years. And under that pressure, life did not stand still. Some groups, highly specialized and finely tuned to previous conditions, declined and disappeared. Others, more flexible, more adaptable, expanded into the spaces left behind. This pattern is visible across both ocean and land. It is not random. It is a consistent biological response to environmental change. What matters is not simply that the world became warmer. It is that the conditions defining survival were rewritten. In such moments, extinction and opportunity are closely linked. The disappearance of one group creates ecological space for another. Over time, this leads to entirely new structures of life, new food webs, new dominant species, new balances. And this is the deeper message. When environments shift, life does not simply vanish, it reorganizes. Not all lineages persist. Not all ecosystems recover in the same form. But across geological time, the continuity of life is maintained through change. The world of the late Cretaceous was not lost, it was transformed. At the beginning, we asked a simple question. What if summer never ended? On the surface, it sounds inviting. Steady warmth, no harsh winters, a world in constant bloom. And during the Cretaceous, Earth came closer to that state than at almost any other point in its history. But as we've seen, a world without limits is not a world without consequences. Sustained heat reshaped oceans, restructured ecosystems, and altered the course of life itself. The lesson is not that warmth is inherently destructive, but that even the most familiar conditions, when extended beyond their natural range, can drive profound and irreversible change. If you found this journey into deep time meaningful, subscribe and join us as we continue exploring the forces that have shaped life on Earth.